Welcome to video module 2 for our simulation-based planning and scheduling course. In this module, we will focus on a set of initial job shop models, and we'll develop several models over the course of this video module. In this first video, we'll talk about what a job shop is and some of the relationships between job shops and flexible manufacturing systems and things like that. And we will develop our baseline model using Simeo. And then in subsequent videos, we will augment that model to add planning and scheduling features and several other Simeo features that we'll use throughout the semester. So what is a job shop? Well, I got this picture from Wikipedia, and you can have a look at this site if you want more details. But essentially, we are talking about process-oriented layout versus a product-oriented layout, as you can see here. And so in the models that we did in the previous video module, we focused on a serial manufacturing systems. And so the flow was essentially defined by the product. And so the parts or products that we were modeling all followed the exact same flow. In a product-oriented layout or product-oriented system, the flows can be different. And so in the example that we see here, we have the different part types. We have I guess this is yellow, the yellow circles, and it goes from machine 1 to machine 2 to machine 5 to machine 6 and is completed. The blue circles go from machine 1 to, looks like machine 4 to machine 3 and they're finished. The green circles go from machine 2 to 3 to 5 and are finished. And then finally the red circles go from machine 3 to 2 to 6. And so you can see that you have the configuration is set up so that you can facilitate a variety of different flows. And so when you think about the characteristics of these types of systems, flexible manufacturing system, or actually a job shop is what I was talking about first. A flexible manufacturing system is a type of job shop, which I'll talk about here in just a second. You have to have flexible machines and processes because the machines are processing different part types and in different sequences. So if I look at machine 2 here, for example, it's processing the yellow part types, the green part types, the red part types at different locations within their respective processing sequences. As I said, the parts have different processing sequences, and these sequences can include different processing times and different setup requirements, different operator requirements, and so on. So whereas the yellow parts, the red parts, and the green parts all go to machine 2, the processing characteristics such as the distribution of processing time, or the variance of the processing time, or the setup time, and all of those things can be different, specified by part type. And so that's important. And then the hallmark of these type system here is this next point where I said these different part types are processed in the system at the same time, right? And so in this system that we have pictured here, we can envision having yellow parts, blue parts, green parts, red parts, all in the system at the same time. And so as a result, the planning process has to be done at operation time as opposed to design time. Because if I have a product-oriented layout, like an assembly line, for example, I can optimize the process at design time. So when I lay out the system, when I configure the system, when I set up the setup rules and tooling and things like that, it can all be done at design time. On a job shop type system, it can't because we have these different part types. And so you have to make those operational decisions and the opportunity for optimization is at the planning and scheduling stage rather than at the design stage. Another characteristic of job shop systems is you have a high mix, low volume environment. And so what we mean here is the high mix means I generally have a whole bunch of different things that are processed in my system. So I have a mix of parts that are processed. Low volume means that for each one, I'm producing a relatively low volume. And so this is as opposed to an assembly line, for example, where you generally have a low mix. So I might have more than one type, but I generally don't have a whole lot. So I might have different colors, or I might have different packaging or something like that, but I generally focus on a single family of part types, and then I have very high volume. So with a product-oriented layout, again, we have a low mix and high volume. With the process, I got these both product here, so I'm going to fix that. So the product layout is serial, the process layout is job shop. So I'll go back and fix that here in just a second. And then we have this high mix and low volume. So the related concepts, I've mentioned FMS or flexible manufacturing systems earlier. An FMS is generally thought of as an automated job shop. So I have automated transfer of parts or part batches within the system. So I'm going from machine 1 to machine 2 for the yellow parts, and that's happened by something like an AGV or a conveyor system. So I generally don't have people moving those things back and forth. And also the setup and tooling is generally more flexible, and so all of those processes can also be done in an automated fashion. The second related concept is the job shop scheduling problem, which we talk about in class a little bit. I'm not going to talk about it much in this video, but it's a classic OR type scheduling problem, and there's lots of literature on the job shop scheduling problem. And so again, I'm not going to focus on that in this video because we're not going to use it, but it's something that we'll talk a little bit about in class, or have already talked a little bit about in class by the time you'll be watching this video. And if that's something of interest to you, there's a huge body of literature on that job shop scheduling problem. Okay, you can see that I fixed my typo here. And so a job shop is the process-oriented layout, and the serial assembly line is the product-oriented layout. And so we're going to look at a specific example for our models. And here that is. You can see that I have 4 different stations, S1, S2, S3, S4, and I have 3 different part types. And so P1 starts at S1, goes to S2, goes to S3, then S4, and then is finished. Part 2 starts at S3, goes to S4, then S1, then S2 is finished. And part type 3 goes from starts at S2, goes to S4, and then it's finished. So P1 has 4 processes, P2 has 4 processes, and P3 only has 2. And then you can also see the average processing times by station. So P1 spends on average 12 minutes at S1, 7 minutes at S2, 11 minutes at S3, and 6 minutes at S4. And so note that this table structure doesn't provide all the information. Right? I also need the routing. So for example, P2 from the table structure looks like it's 10, 12, 14, 10, but remember it follows a different sequence. So its first process will actually be 14, second one 10, third one 10, and the fourth one 12. So this is the simple system that we're going to develop our first model for next, and then we will, as I said, we'll expand this model in subsequent videos. Before we build the basic model, let me comment that our example system is extremely simplistic for a job shop. We only have 4 processes, and we're only modeling 3 part types, and a general job shop would be much bigger. In other words, I would have most likely more than 4 processes, and I would have multiple units of the individual process type. So instead of having a single S1, I would probably have multiple copies of S1. And the system would include things like setups, operators, if it's a job shop, automated transport, if it's a flexible manufacturing system, and so on. So we're not considering any of those things in this model. We will in the future. What we want to do is start out with a very simplistic model to talk about the basic structure, and then those same principles that we talk about throughout this video module will be applicable for those larger systems that include those additional complexities. And we will see some of those additional complexities in subsequent video modules. For our baseline model, we're going to have some assumptions. First of all, we're going to assume that parts arrive at the rate of 6 per hour. And so we have an inter-arrival time, and these are Poisson arrivals. So we're going to have inter-arrival times are exponentially distributed with a mean of 10 minutes. Part types are selected randomly, with all 3 being equally likely. So we have an arrival process with a lambda value, or an arrival rate of 6 per hour, and then we will choose randomly which type it is when a part arrives. We'll assume that we have infinite buffer capacity at the stations, and that the individual stations operate on first in, first out basis. As I mentioned, parts in our system, in our baseline model, don't require any kind of transportation resource. So I don't have AGVs, and I don't have conveyors, I don't have people who move the batches. Parts are just going to move automatically. And we're also going to assume that that transfer happens instantaneously. Again, we'll come back and relax some of these assumptions in subsequent modules, but in this particular module, we're going to make this no transportation resource and instantaneous travel assumption, and we'll discuss that as we go a little bit why we're doing that. So note that while we assumed the inter-arrival times are exponentially distributed, we haven't said anything yet about the process times. We noted that the process times were specified in the table on the previous slide. We will in fact assume that those are also exponential, so we'll have some typical queuing analysis that we will do in the next video. I didn't mention it here because we're going to implement that through the use of sequences, which we'll see here in just a second. And our objectives here are to determine some steady state values. We'd like to know the station utilizations, the average number of parts in the system overall. So we have 3 different part types, and we're going to have this sort of generic average number of parts. And then the average time that a part spends in the system across all 3 different part types. So what I'm going to do is talk a little bit about the strategy for our Simeo model, and then I'll switch to Simeo and we'll actually build this model. So our strategy is going to be pretty straightforward. We're going to use server object instances for the 4 stations. We're going to use model entity instances for the different part types. We're going to route entities by sequence. So recall in the serial system that we did in the previous video module, we didn't really have to think too much about sequence because all the parts followed the same sequence. And so we just connected the stations with connectors, and that was it. In this system, parts have different routes or different process flows, so we need to have a mechanism in Simeo to implement that. And the mechanism that we're going to choose is to route them by sequence using a sequence table. We're also going to have the entities move from station to station through free space. As I said, we could implement this with connectors like we did with the serial system, where I connect the previous station to the subsequent station with a connector. But in the job shop system, what that would make me do is basically have a complete network of connections. So if you think about our system here, let me go back. S1 would have to be connected to S2, and then to S3, S4. S2 would have to be connected to S1, S3, S4. So when I say completely connected, you can think about this in a graph context, is that I have these 4 nodes and I would have to have those complete connection. And so we don't want to do that. You can do that, but what we want to do is going to reduce the clutter a little bit, and so we're going to have the entities move through free space. And then we will use the preliminary evaluation of the performance metrics simply using the pivot grid. In the next video in this module, we will, in the verification process, develop an experiment, but in this video, in this particular video, all we're going to focus on is using the pivot grid. So here we are in Simeo. I'm in just a pristine version of Simeo. I don't have any model pre-built or anything. And so what we're going to do is just walk through the building of it. It's a relatively simple model, so it won't take very long. And you should definitely follow along and do this with me or while you're watching the video, where you can stop the video and rewind as necessary and so on. So as I said, we're going to represent the processes, the stations using the server object. So the first thing I'm going to do is grab 4 of these. So there's S1, S2, S3, and S4. And then I'm going to go back and rename them because I want to use, oops, that's not S2, that's 1. I want to use a standard naming convention here. So that's S1, and there's S2, there's S3, and finally S4. So there are 4 servers. We're going to create the entities using a source object instance, and then we will send all of the entities to the sink once they've completed processing. I have 3 different part types, as I said. So we have P1, so we'll do a model entity instance for P1, a model entity instance for P2, and a model entity instance for P3. And then I'll go in quickly and rename those also. So there's P1, P2, and P3. And then I'm going to use different entity colors. So I'm going to go over to, select my entity instance, go to color. We'll have green and red, and then we'll make P3, I guess this light blue color. So we have P1, P2, and P3, and then that's the basic physical structure of our system. We're going to use part sequences, as I said, or entity sequences to route the entities. So I need to create the sequences. I'm going to have one sequence for P1, a sequence for P2, and a sequence for P3. And so back to our slide here for just a second. The sequence for P1 is going to be S1, S2, S3, S4, the sync. The sequence for P2 will be S3, S4, S1, S2, and then the sync. And then finally the sequence for P3 will be S2, S4, and then the sync. So we go back to our model, and I'm going to implement this using two related tables. So I'm going to go back to my data tab, and I'm going to use the add table, and I'm going to name table 1 parts. Oops, get off the 1 there, name this parts. And our parts table is going to have two columns. I'm going to have an object reference property to our entity. So this is going to be, we have 3 entity types, and so this is just going to be the part. And then I'm going to have a property so that I can specify the mix so that I can use the random row property in the source to generate random observations. So I'm going to let me put that in here, and then we'll talk a little bit about that. So we'll just make that real, and we will call that mix. There we go. We have 3 part types. So we have P1, and I stated in the problem assumptions that we want all parts to be equally likely on an arrival. And so all we have to do that with the part mix, once we set the source appropriately to use this mix column, is make sure that these are all 3 the same number. It doesn't have to be 1, it could be 2, it could be 3, it could be 100, it could be 14.78, anything as long as they all 3 have the same value. Because recall that the random row function takes the sum of these, the sum of the values, and then divides that into the current value. So if I want to know what the probability of a P1, I take this value 1, divide that by the sum 1/3. I do the same thing for P2, 1/3, and so on. So you can control the relative probability easily that way. So then next thing I'm going to do is I'm going to set this as a key column so that I can use a related table for the sequence. Okay, so now we have our parts defined, and I could go back and go to my source and say I want to have the, let's see, table row reference. It's going to be create row reference. It's going to be the parts table. So there's my parts table, and here's the row number where we'll use that product mix. So we're going to do parts, mix, random row. There we go. So we have random row. And then the last thing I need to do is specify that the entity type that's created is based on that the parts table. So that's just going to be parts. There we go. And so now you can see the green arrow, green arrow indicating that is a reference property. Okay, so now we will create. So we go here, create, and so I can go back to my source, and if I were to go and say, okay, well, let's go ahead and change this to our in-arrival time. So we know that's going to be 10 minutes. So just go ahead and change that guy right there. And then it's going to create part every 10 minutes. Exponentially distributed for the in-arrival times, and then those part type that gets created will be chosen randomly. So at this point I could run my model. We haven't done anything about the sequence, but as entities will get created, and recall when entities move through free space, if you haven't specified anything else, they just go to the closest object. And so that's what you see happening here is I created a red one, and then the closest thing that it had was S1, so it went to S1. When it left S1, the closest thing to S2 is S3, and so they just oscillate back and forth. We could let this run for a while, but I'm going to stop that because it's pretty boring. First of all, we have a long in-arrival time relative to the speed factor, and we would just see new parts getting created and oscillating here. And so what we want to do next is implement the sequences, and then we can go back and look and make sure that entities are being created as we expect. So the distribution of in-arrival times, the relative proportion of 1/3, 1/3, 1/3, and so on. So again, we're going to implement our sequence or our routing using sequences. So I need to go back to my data tab, and then I'm going to create a second table, and my second table is going to be a sequence table. So I do the pull down and say, okay, I want to do a sequence table, and you can see that a sequence table is just a standard Simeo table, except it has a column that is a sequence destination property. So that's what makes a table a sequence table, is any table that has a sequence destination can be a sequence table. So that pull down here is simply a shortcut for creating a table and then adding such a column. So we're going to call this sequence table sequence. Let's just call it sequence there. And then we need to link that back to parts. And so our second type that we need, or our second column that we need, is a foreign key property. So remember, we made the part column a column key. So go back to my sequence and I want to add a foreign key property. We're going to rename that part. And then the table key that I want to use, of course we only have one, is parts. Okay, so there's our parts. So now we have the column key. And so now we can define our sequences based on part. So by convention, at least for my convention, I like to have the column key over on the left. So I'm just going to move that guy left. There's no operational reason to do that. Just have it on my part. And so we can define the sequence if I just say P1, and P1, recall, goes from S1. P1 then goes to S2. P1 goes to S3. P1 goes to S4. And then P1 goes to the sink. So that's how we define the sequence for P1. And because they're related tables, I can go back to the part table and then click on the plus, and now you can see the sequence for P1, S1, S2, S3, S4, and the sink. Okay, so let's put the other ones in. So P2 is going to start at S3, and then P2 goes to S4, and then P2 goes to S1, P2 goes to S2, and then P2 goes to the sink. Then finally P3 goes from P2 to P4, I'm sorry, S4, then to the sink. Okay, so I find it easier to look at in this related view, so I'm going to just open that one, open that one, open that one. P1 is 1, 2, 3, 4 sink, that's correct. P2 is 3, 4, 1, 2 in the sink, that's correct. P3 is 2, 4 sink, and that's correct. Okay, so I think we have our sequences set up correctly. And so now we need to do one more thing. Go back to our model, facility view, and set all of the transfer nodes where entities are transferred to use the route by sequence option. So I'm going to just go here. So if you just pick from the source, so when an entity is created, we go over and look at this entity destination type, and we just need to choose by sequence. Now, the reason we didn't have to say, for example, that P1 has a sequence or P2 has a sequence, we didn't have to actually assign it to that. So in other words, if I go look at P1, I didn't have to give it an initial sequence because Simeo knows that it had that sequence table. So when you create the entity using the table, set the table row reference, because that table row reference to the parts table is related to the sequence table, Simeo knows that that is a sequence, and so it's going to apply the corresponding sequence based on that part row reference. So we need to do the same thing at all of the stations. I'm going to do this by selecting them all four. So I'm just holding down the control key, selecting all four of the transfer nodes, and then go here and say by sequence. So hopefully when we start the model, we should see parts being generated randomly. The type should be random. The green one should go S1, S2, S3, S4, the sink. The red one should go S3, S4, S1, S2, S-sink. And the blue one should go S2, S4. So I mentioned before that, or back in the assumptions, that we want entities to transfer in 0 time, so we want them to transfer instantaneously. So I'm going to come back and do that, but I'm going to leave the entities at their default speed, which is 1.4 meters per second, just so that we can do some preliminary verification, so I can make sure that I've actually implemented this correctly. So when I hit go, let me speed it up a little bit because we have a relatively long arrival time. We just saw the red one, which is P2, go 3, 4, 1, 2. So we're sort of satisfied with that. At least so far I'm satisfied. There's another red one. I think I remember from previously we had a whole bunch of red ones. There's some green ones, and so on. So we can see them running, but it's running pretty quickly, because I haven't set the processing times. Recall, if you look at the processing times, those are still relatively small. So it's a little bit difficult to see what's going on. You can leave it, you could do some additional verification, let it run, experiment with the speed factor and so on. And this is something you should definitely do as you're building models, is continually, as you add new functionality, go through the verification process. I'm not going to do that right this second. What I'm going to do before I do that, again, is go in and implement the processing times. And so recall the processing times again from our table. We have 12, 7, 11, 6 for P1, 12, I'm sorry, 10, 12, 14, 10 for P2, and 9 and 11 for P3. And I'm going to implement those expressions. So we want these to be exponentially distributed. And I'm going to implement those expressions in our sequence table. Okay, so I'm going to specify the processing time expression within the sequence table itself. So in order to do that, I need to go to my sequence table, add a property, make sure we choose expression property, and I'm going to call this property p-time. And I want to specify the unit type here because I want this processing time to be in minutes. So I'm going to specify that processing time in minutes, and if you expand this column a little bit, you can actually see it's going to say p-time in minutes. Okay, so I said I wanted these to be exponentially distributed. So instead of typing these, I'm just going to cut and paste from a different window here. So there's my random exponential 12. If you get the columns to work right, this would be less annoying. Random exponential 12. There we go. And then the second one is random exponential 7. Paste that in. Random exponential 11. Random exponential 6. So there's my 12, 7, 11, 6. And then I'm going to, we don't need to have one for the sync because obviously there's no processing that goes on at the sync. The second one is, let's see, for p-type 2 is 10. The third one is also 10. And the fourth one is 12. So paste, copy that. And then we, of course, don't have to have that one as 0. And then for P3, we need 9 and 11. And it doesn't need a sync. So again, if you look at, go back and if you were to go look at the table, we have 12, 7, 11, 6. And then if we look at our Simeo model, we have, oops, if I can find our Simeo model here, right there, 12, 7, 11, 6. Follow the same process of verifying these and so on. Okay, so we have those specified in our table. Last thing we need to do is specify that we are using the processing time at the stations. So again, I'm going to select all of these because I want to have the same thing in all of them. I'm going to tell you the processing time is determined by the sequence table p-time. And so again, the reason this works, where I have 4 different stations and 3 different part types, is that when we set the row reference, so when we set the row reference when the part's created to the part table right here, then it has a row reference that propagates to, let's see if I can get this here. Oh, sorry, clicking the wrong thing. It has the row reference that propagates to the sequence table. So when the entity hits a transfer node, like when it leaves the source and it's route by sequence, the sequence is initiated here. It then will route it to input at S1. And then because it has this row reference set, when I have sequences.ptime, it will sample from this distribution, or will in fact use this expression. And so now when I go back and run my model, we're going to see the processing times are a lot longer. And so we'll be able to actually watch what happens here a little bit. So let me go back there and I can speed this up a bit. Maybe see a little bit more happening. So we can see the red one. Now we have a green one and there's a blue one. And hopefully the blue ones are just going here to here. And the green ones are going 1, 2, 3, 4 to here and so on. That all looks to be like it's working. If one thing that I could do if I wanted to do a little bit more looking at that is I could go and slow these down, right? So we have these operating initial desired speed of 1.4 meters per second. Let's say that I cut that to 0.25 meters per second. And now we can actually see, even though we have the speed factor pretty high, we can actually see the entities moving. And so we could watch that and make sure that they are in fact moving in the sequence that we specified. So just a couple more things to do to our baseline model, but before I do that, let me remind you that, as you build along with the video, you should be experimenting with this model. You should be stopping the video and running and doing the things that I'm describing, change the speed, do some more face validation, and so on. Rest assured that I do that when I put the videos together. I just don't include all of that in the video. So experimentation or doing it continuously through model development is really important. Okay, so the two last things that I want to do, the first one is I want to set these speeds to infinity. We said that we have transfer happen in 0 time. So when I click go again, you can see these moving through free space. But what I want to have happen is them to move in 0 time between entities, or I'm sorry, between stations. So I can do that by just setting the speed to infinity. Right, so I can set the speed to infinity, and then they'll of course travel in 0 time. Note that depending on when you took Simeo, this feature might not have been available. So the ability to set speed to infinity is a relatively new feature, so you might not have seen that. And so now when I run, you can see we don't see any entity movement. All we just see is the entities jump as we expected in 0 time. Okay, so the last thing I said I wanted to do here is that if we look back at our performance metrics, two of the performance metrics that we're interested in is the average number of entities in the system at steady state and the time that entities spend in the system at steady state. And we have 3 different entity instances. So the default Simeo statistics will be computed or collected by entity type. And what we want is an overall statistic. So I'm going to do that really quickly. We need to create a state statistic. So I need a state so that I can track how many entities are currently in the system. So I'm just going to do that and call that number in sys. So number in sys is a model state where at any time in simulated time, that will represent the number of entities currently in the system. Then I'm going to go and create a state statistic. So just go to my elements, state statistic, and I want to do number in system. Oops, did I call it number in sys? Number in sys, yeah, there we go, number in sys. So all I have to do is specify what state I want to track, and I'm going to call this just capital NIS. So now I have a manual state statistic tracking that value, and now I just need to make sure that the value is set correctly. And so that's relatively easy. As soon as an entity arrives, I'm going to do a state assignment before exiting and just say, pull this guy over here, and this is going to be number in sys, and it's going to be number in sys plus 1. So we're going to increment the value here. Similarly, we will go to the sink and we will decrement the value there. So go to state assignments and add a new state assignment, and we want to do number in sys and number in sys minus 1. Okay, so now that number should be tracked. As the simulation runs, whenever an entity arrives, we increment the value. When an entity departs, we decrement the value, and then we're telling Simeo to track this state over time. All right, so one last thing I want to do is I'm going to add a status label here so that I can track the number of entities that go through the sink. So the expression that I want to use, note that it's an attached status label. So I just have to do input buffer number entered. There we go. And now when we run our model, this number should increment every time we create an entity. There you go. There's our first one that went through. And if I can just speed this up a little bit and just make sure that we're actually seeing this incrementing, it looks relatively good so far. Okay, so I said we wanted to, for this model, for this video anyway, we're just going to use the results tab. So I'm going to set a run length, and I'm going to make this, I don't know, let's make this 1,000 hours. Just run for a little while, 1,000 hours, and we can run. And then at any point, we can decide we just fast forward. You can see time going here, so we'll just fast forward. There we go. Now when I look at my pivot grid and my results, you can see it's compiling those. We have these standard performance metrics. And one last thing that we'll do is I want to filter that because I'm interested in particular values. So I'm going to just go do a filter to the data item, And instead of showing all of those, I'm going to have the number in system, the scheduled utilization, and the time in system. That's what we wanted. And then I really only care, at least for now, about those average values and then the percent value for the utilization. And so you can see by filtering those, hopefully this is, I'm just reminding you of this, we can see those performance metrics that you're interested in. We're interested in the utilization here of our 4 stations. We're interested in the average time that an entity spends in the system and the average number in the system. So we can see the average time in system here as based on the sync. I don't see my user statistic here, so I got to go back and put that in. Let's see. I guess I filtered away from it. Let's see. Where is my user statistic? Let me show those all here just a second. Go back. There's my state value. Here's our average number in system here. So I guess that is a state value as my data item. Okay, so I'm not going to refilter them in the video. I'll do that offline, and that's something that, again, you should go back and do, make sure you understand the basic concept. Okay, so that concludes this first video in video module 2. In the next video, we will talk about verification, use a queuing model, develop an experiment, and do a little bit of experimentation.